Okay, let's get started. Any questions in the last class of new material? Unless you feel really eager and want new material on Monday too. Okay. Any questions on last lecture or anything? Feel Wednesday coming up? Then you can finally celebrate. Hopefully you can celebrate. But yeah.
I have a more general question. Whether I know we've talked about P versus NP being open questions. What are some of the other open questions we've already discussed?
The one about NP and co-NP from the recitation. So like the complements of the languages in NP. So we don't know whether NP is closed under a complement or not. So that's another open question. But of the questions we considered, none of the other ones are open. But there are, for example, some open questions about even decidable languages or even regular or context-free that I know as well. But I can give one to you if you want as an example. But so we know that the language of prime lengths is not regular or even context-free. But consider this problem. So this is open. If you can solve it, then please talk to me because maybe we can get a paper published. But consider this language. So it's so now all we're considering is a DFA. We're not going to talk about Turing machines or anything. So D is a DFA with language of D. Oops. So the language of D is just zeros and ones, right? So it's just a binary language, no problem there. And D contains some string W that encodes a prime number in binary. So I give you a DFA and over 0, 1 star, and I want to know whether or not it has some string that contains a prime as in binary or not. And no one knows whether this is decidable or not. So this is another open question. I won't ask you about this on the final. I guarantee you that. But it's a pretty cool question that people still don't know the answer about DFAs. If, for instance, I change this to 0 star instead of 0, 1 star, then this is decidable. But we don't know whether it is for binary versions of primes or not.
How do you encode a prime number with only zeros?
Prime lengths.
Oh.
And it's actually pretty simple because so this is getting into something I wasn't even going to talk about today. But if you think about it, if you have a DFA with just with only one character in the alphabet, then what either happens is that it's always a straight line because you can't have any other transition like that. And then what must happen is either it's a straight line that goes to a final or a non-final state, or what it does a big long loop and comes back and then plugs into some state before. And then if you think about it, these are what are called arithmetic progressions. Because if you have, for example, 7 transitions in this loop that comes back, then it's basically, if you keep adding 7, you're going to get all of the other strings in the language because it can't accept anything else. So you can actually heuristically say whether or not there's a prime in there because it's just, is there a prime within this arithmetic progression? That sort of thing. So it's actually a pretty cool question, but I don't know the binary version. We will hit some more open problems today. Other questions? Yeah, I definitely won't ask you about this. Okay, any other questions? There are whole swaths of open problems like this too, but this is the one that I know best. Okay, so what were we talking about last time? P-space, right? And then what was the big important result that we were able to show last time, right at the very end? The Savage's theorem, right? So we saw this theorem by Savage, which established that as a result, or it implies that P-space is equal to NP space, meaning that it doesn't matter whether or not you use determinism or non-determinism with respect to polynomial space. So if you have a deterministic polyspace machine or a non-deterministic one, it's still in P-space no matter what. So you can convert it back to a deterministic machine with still polyspace. So, and with not too much of a slowdown there. So that's what we were able to show last time. Any questions about those two? And of course, we don't know whether P equals NP. But what was one thing that we have done for NP, but we haven't done yet for P space or NP space? We haven't talked about complete problems, right? We established an NP complete problem, and actually several, but we haven't talked about a P space complete problem, right? And maybe that could help us determine whether or not NP is different from P space. So let's actually, as a warm-up, show a relationship between NP and P space. So non-deterministic polynomial time versus polynomial space. So just as a quick result, we'll show that NP is a subset of P space. And an open question here, so going back to your question, is this strict containment? And no one knows the answer. And in fact, we don't even know whether P is different from P space, let alone NP and P space. But yeah, this is an open problem. So why is this true? Or why do you think this is true? Well, if I can simulate an NP complete problem in polynomial space, is that all I need? Well, if I want to solve any problem in NP, whether or not it's NP complete or whatever, I can just transform it via a polytime reduction to an NP complete problem. And then if I can solve that one in polynomial space, well, I incurred a polynomial blow up in the size of the input, but that's still a polynomial amount of space. So what's our favorite NP complete problem? 3-set. I could use any NP complete problem here, but 3-set's a good one. So just as a quick proof, 3-set is in P space, which would show this containment. So why is this true? And could I solve 3-set in polynomial space, but unlimited time? I'm not limited amount on the time here, just the amount of space I use. So what method could I do? Yeah. Oh, I thought you raised your hand. What could I do to run this in polynomial space? What about the brute force idea? Just try this assignment. If it works, great. It's satisfiable. What if it doesn't? Throw it away. Reuse the space. Try the next assignment. Then try the next one. Then the next one. Then the next one. All to the end of them. Well, do I need more than polynomial space? No, in fact, I only need linear space for that, because all I need is to write down the truth assignment and then evaluate the formula. And then I can do that easily in polynomial space. So we can, because we can brute force all possible assignments variable assignments, I mean, in polyspace. So in fact, because of this, we now know that P is a subset of NP, which is a subset of P space. And P space is equal to NP space via Savage's theorem. So I'll just write that down. So P is a subset, actually I'll just write it below. So P is a subset of NP, which is a subset of P space, which is equal to NP space. Great. Any questions on that? Should be relatively straightforward.
So just checking what I mean. So because you can reduce any NP complete, or any problem in NP to 3-sat?
Mm-hmm. Well, by definition, yeah, because it's NP complete. Mm-hmm. Cool. So we haven't talked about an P-space complete problem yet. So let's just establish what completeness here means. So we're just going to define it in exactly the same way, but the only difference is that now we require the languages to be in P-space versus just NP. So a language L is P-space hard if for any B in P-space, we're going to do the same reduction. B poly reduces to L. And then, as you might expect, we'll say that it is P-space complete. What do you think I'll write next? Is P-space complete if? If it's P-space hard and in P-space, yes. So if L is P-space hard and L is in P-space itself. Got to be in the class to be complete for the class. Cool. So do we have a P-space complete problem yet? No. So so I'm not going to do all of the details as the Cook-Levin theorem was for, but I'm just going to sketch the idea. So the problem that we're going to consider is called TQBF, and what it is a generalization of 3-sat. So for 3-sat, or any sat problem for that matter, we just ask, is there a way to set the variables to make the formula true? Right? Is there a way to satisfy the formula at all? Well, here what we're going to say is we're going to allow that possibility, but for some variables, if you like, we're going to say for both possible ways to set this variable, either true or false, both of them must still allow you to satisfy the formula. So instead of just saying there exists either true or false for which this variable allows you to make the formula true, we're going to allow you to also say for both possible values for this variable, the formula still has to be true. Okay? So this problem is called TQBF, and I'll define everything here. So TQBF stands for totally quantified Boolean formula. Okay, so what we're going to have here are quantifiers, and the ones we will have are exists and for all. So how are you going to use these quantifiers? Well, if we write, exists x with phi, and phi is a formula, and x is a variable, then there must be some way, either true or false, to assign x such that the formula can be made true. So then this means that exists and assignment to x such that so here I'm going to introduce a little bit of notation. So phi with this vertical bar and x on the bottom all that means is phi restricted to x. So here, if you pick, say, true for x, then if I plug in true everywhere I see an x, or if there's an x bar, I put a false. If I just plug it into the formula, then the resulting thing is true. So I'm hard coding the values into the formula. So if there is a way to set x such that the formula is true, then we say that there exists an x for which the formula is true, so the whole thing is true. But if we do instead for all x, phi, then what do you think this is? For all x. Both possible ways to set x, yeah. So for both assignments to x, assignments to x, phi sub restricted to x is true. Okay, so let's just do a quick warm-up. So if we consider not just, and of course this can be extended to anything other than Boolean formulas as well. So for example, if phi says something about, say, the natural numbers or the integers or something, and I ask you the question, exists x for which this is true, then there exists a natural number for which the statement is true. Or if I have a for all here, then for every possible natural number, the formula is true, with something relatively related to natural numbers. So as an example, if we considered this formula for all x, and then the formula itself is x plus 1 is strictly larger than x. So it says for every natural number x, x plus 1 is larger than x. Is that a true statement? Yeah, there's no counterexample to that. Every possible x, x plus 1 is larger than x. What about this one? Exists a y such that y plus y equals 3 over the natural numbers. No, because the result is even, y plus y is even, but 3 is odd, so there can't be. But if I change this to say rational or even real numbers, then this statement is true. So it depends what is called the universe you're working over. But here, just for TQBF, we're just going to restrict ourselves to Boolean formulas. But as you might expect, you can generalize this if you wanted to, and then maybe say something a little bit more. And there are whole fields about this sort of thing about, so there are grad classes here that you can take about knowledge representation and whatnot, and they go over this type of thing where if you have this particular universe, then this problem is decidable of whether you can check whether the formula is true, and some other ones for which it's not decidable, that sort of thing. But let's get back to Boolean formulas. So TQBF here, and I'm going to make one more definition I just remembered I need to make. So we're going to say that a quantified Boolean formula is, so what's the word for it? Oh yeah, is in pre-nex normal form if all the quantifiers appear first. So it's not like you have a quantifier somewhere and then a whole bunch of the formula part and then another quantifier on the inside and then some more formula and then the quantifier. We're just going to stick all of the quantifiers right at the very beginning and then the rest of the formula without any quantifiers on the inside. So note that this, a special case of this is 3-sat, because if you just set all of the quantifiers to exist, then that you're just asking, is there an assignment to these variables to make the formula true? So this seems at least as hard as 3-sat. So, and that gives you an indication of why it's p-space complete, but we're going to get there in a sec. So TQBF here is, so I'm going to denote the formulas as psi. So psi is a quantified Boolean formula. So psi is a quantified Boolean formula in pre-next normal form. That is true. So the Boolean formula is true. So there is a way for all the exist variables and for every way to assign the for all variables, then the resulting formula evaluates the true. Okay, so for example, if we were working over the natural numbers, for instance, this formula would be in TQ, I guess, natural numbers F, and this one would not be, as an example. Okay, so I want to show that this is, in fact, a p-space complete problem. Okay, so how would I show that it's p-space complete? Shows it in p-space and it's p-space hard. So how can I do show it's in p-space? So this is actually a little harder than it might seem at first. The 3-sat version is easy, you just keep trying all the assignments. But here, I may have some for all quantifiers, and I need to actually keep track of that. And if I'm just trying all assignments, I don't necessarily have a way of checking that. And if I just list all possible ways of looking at the for all variables to make the formula true, then I might have an exponentially large number of things to write down. And I'm restricted to polynomial space. So I can't necessarily just write down all the for all possible assignments and then just try them all. We got to do something a little more clever. So let's see. So if, note that it's in pre-next normal form. So the quantifiers appear first and then the formula. So let's just say that it's like exists x1 for all x2, exists x3. This is actually a different form where you alternate quantifiers, but I'm not going to get into that. And then maybe the last one's an exists. And then the formula over here. Note, if I figure out there is some value of x1, then couldn't I just work on this formula from the rest of it? So if I just look at, oh, maybe I'm going to hard code x1 to be true, for example, then couldn't I just restrict my attention to fixing x1 to be true and then working on the smaller thing? And then maybe the resulting thing, if I do this recursively, maybe it doesn't work. Then what should I try for x1? I try the other one, right? And then I recursively go down. If I get to a for all, so let's say I dig one level deep here. And if I get to a for all, and then I try, say, setting x2 to be true, and then I do this recursively, and then let's say the result is actually true. Then what do I need to do? Try it on the other one, on the other assignment for x2, and then do it recursively again. What if on that first recursive call for x2, it actually said, no, the formula is not true? Then there's no way to make this formula true, right? Because it says for all of them, it has to be true. But we just showed a counterexample to that for all. So in fact, the formula is not true. So in fact, well, what do we actually need here? Well, I need to keep track of, okay, I set x1 to be true right now, and I'm currently setting x2 to be, let's say, true, and then x3 to be maybe false, and then x4 something, yada, 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 all the way down. And then what do I do on the formula once I fix all of the variables up here? Just evaluate the formula, right? If I evaluate the formula, then it may or may not be a true formula, right? Well, how much space did I incur writing down those assignments? Well, I only need 1 bit for each one of these, right? Because I only need to write a 1 for maybe true, 0 for false. Well, how much, so ignore the quantifiers for a second. So clearly I can do the quantifiers writing down whatever assignment I'm looking at in polynomial space. That's no issue. What about the formula itself? How much space does that take to evaluate the formula? Well, I'm fixing all the values, so I just substitute into the formula the values, and then I just work with the formula right there. I don't need any additional space. So in fact, I can do this in polynomial space. So here's the idea. So T is, so if we get some formula psi like this that has the quantifiers out front, well, if this formula, whatever it is, has no quantifiers whatsoever, has no quantifiers, then we just evaluate the formula whether it's true or not, right? If we just plug in the values, if there are no quantifiers in this formula right now, maybe there are other ones we've already considered, then the formula either is true or it's not true. So we accept if and only if the formula is actually true, because it has trues and falses in it, so the entire formula is either true or false. There's no, it's not like we're testing assignments here. It's a constant formula. There's no variables here. Well, if it has a quantifier, it's either an exists quantifier or a for all quantifier. Good. So if this formula is of the form exists x1 phi, then what do? Then recursively call with x1 set to true, and then again with x1 set to false. If either call returns true, we accept. Otherwise, reject. Okay, so it's just a simple recursive algorithm here. And why does this run in polynomial space for this part? Because if we do the recursive call and then maybe the answer is true, then I can delete that entire call stack going down. So in fact, I'm reusing the space like we've seen how to do before. And then I can reuse it for the other call, for the when I set x1 to be false. And then, so that works for the exists case. What about the for all case? Well, what has to change between the exists and the for all case? Yeah, here we just need to accept if and only if both tests pass. So same, but except if and only if both recursive calls pass. And that's the whole thing. So it's just recursive, right? If we have the quantifiers out front, just look at the first one that you haven't looked at yet, and then if it exists, try both assignments and accept if and only if at least one of the ways passes, and then the for all, accept if both of them pass. If one of them doesn't pass, then the entire formula is false. Okay, so it's actually pretty simple because the algorithm is simple and it runs in polynomial space because I reuse the space. So therefore, we can say that TQBF is in p-space. Cool. Any questions about that? So it is a little more non-trivial than the 3-sat one. Yeah.
Why do we have
Because it's just easier to have the quantifiers out front here. Because I'm drilling down out the front. Well, if I have like quantifier, then some formula, and then quantifier there, then I may need to do something here because the part of the formula may be out of the scope of one variable, but in the scope of another, so now I need to handle scoping. Here, I don't need to handle scoping because all the quantifiers are out front. So every variable in the formula is in scope. So in fact, I can actually claim that any formula, any quantified formula, can be converted into one which is in pre-next normal form. So the formula is substantially larger, but and I invite that as an exercise, and I won't test it on it, but we can assume that it's in pre-next normal form here. Yeah.
So if you're in recursion, it's only the maximum height of the tree. So
Well,
the tree that's actually.
Well, it's the number of quantifiers out front, because that's the number of times I need to dig down. Yeah, and so it's therefore a polynomial in the size of the input. Any other questions? Cool. So now, what else do we need to show about TQBF? That is actually P-space hard, right? And for the sake of time and my and your sanity, I'm not gonna do the entire thing. I'm just only gonna do a sketch of it, because a lot of the reduction is almost identical to the Cook-Levin theorem, but there are a few changes that we need to account for because we're working in polynomial space. And whatever language that we're trying to reduce from to TQBF, the starting language was in P-space. So we don't know anything about how long the actual algorithm for that language takes. We know that how much of the tape is being used, but we don't know how long it takes. Okay, so I'm going to do a sketch of the proof that TQBF is P-space hard. So if you remember back to the Cook-Levin theorem, what we did is we built, in some sense, this giant table that encoded a computation of the machine, right? And so we built this giant table. We made the formula such that you must start correctly, you must end with the except state somewhere, and each line in the tableau must yield the next one via a transition. And so the formula there was true if and only if there was some way to set the variables, which means that there was an accepting computation on the input. And so therefore we can claim that 3-sat there was NP hard. But here we need to think a little bit harder. So let's think about it this way. So we're going to build the formula in a recursive way. So we're going to consider the types of formulas that look like this. So the formula we're going to look at is of the form, some formula indexed with C1, C2, and T. And what we want here is this to be true if and only if C1 can yield C2 in at most T transitions. So almost identical to the Cook-Levin theorem, where we had this can yield function with the C1, C2, and T. We're going to build a formula for each case, and then we're going to recursively build up to the entire formula here. Well, whatever amount of space is used, I can actually calculate how many possible configurations of the machine there are. Well, if we're going to reduce L to TQBF and let M decide L. So M is some machine for the language we're reducing from, and it must run in polynomial space by assumption. So M decides L, but I need to give some function here. Well, let's just say it's O of f of n space, where f of n is some polynomial. It's actually not important what it is. Well, the number of configurations of this machine is, well, if you remember back to Savage's theorem, where we had to break the computation in half. Well, we calculated how many possible transitions that might occur, which is just 2 to the power of the amount of space that is actually being used. It's not exactly this. We may need to change the constant upstairs, but all we know is that it's some exponential that looks like that. So from this, we can say that there are at most 2 to the power O of f of n configs M can use, whatever that is. Okay, well, let's try to build the formula recursively. So if t equals 1, meaning I want to be able to build a formula that goes from, I got a configuration C1 already and a C2, and I want to see if I can do that in one step. Can I build a formula for that? Well, yeah, because all we need to do is just check either they're the exact same config, then clearly at most one transition taken to get from there to the same thing, or I just check, does the first one yield the second one via one transition? And because I can just look in M's transition table and say, oh, this one actually does yield this one in one transition. So just check if C1 equals C2 or C1 yields C2 in one transition. So it's almost exactly the same. Cool. So yeah.
So the C1 represent.
It's a configuration.
Configurations and how those in this string going formula.
Remember, it's the tape contents along with the state written somewhere.
Okay.
Yes. So the details are not that important. It's just like the state of the machine yields the next state of the machine.
So are both of those configurations in one formula? Is that what that's
Yeah, yeah. So I'm fixing C1 and C2 temporarily, and they're embedded in the formula.
Okay.
I'm just seeing, can you get the next one in one transition? Okay, well, let's see. So if t is larger than 1, well, I need to say, well, if I can find some middle ground configuration between C1 and C2, if I can find one, then if the formula that represents going from the start C1 to this supposedly middle one and is true, and the formula representing going from here to that C2 configuration is true, then could I get from C1 to C2? Yeah, so informally, if I can get from C1 to this supposedly middle thing, and from the middle thing to C2, then in fact I can get from C1 to C2. So what I need to do is just existentially quantify over all possible middle configurations and then just check, does there exist one for which going from here to here is true and from here to here is true? And then therefore I can get from C1 to C2. So here, so this is what we want, but I'm going to write down a formula that doesn't work. Although it's true, it won't be what we want. So here we're going to say phi of C1 C2t, the thing I want to solve. I'm going to say, well, I'm going to look over all possible middle configurations. So there exists a mid config such that the formula from C1 to mid can be done in at most t over 2 transitions, and going from mid to C2 takes at most t over 2 transitions. So I'm just checking, is there one that works? Then if there is, great. And then therefore the formula on the left side is true because it said, oh, there is a mid such that this works, therefore the entire thing is true. So this formula actually does have the correct value. It's not wrong. So it does have the right value. But why should we not use it? Imagine that we broke, say, this part down one more layer. Then what would happen is, well, I'm going to break this down, but I'm going to get two sub-formulas from it. So every time I'm breaking down the computation, I'm doubling effectively the size of the formula. So if I want to break up the formula in half in some sense, I got to double the formula. So in fact, if I expand all the way down and make the entire formula for this, then it's going to be exponentially large, which is not what we want, right? There are at most this many things, configs. Well, I may need to check all of them if I'm just going to keep drilling down until I hopefully find one that works. So this idea does not necessarily work in polynomial space. Well, that sucks. Well, what could we do about that? Well, both of these have to be true, right? Couldn't we use for all quantifiers for that? I'm allowed to use for all quantifiers, right? Don't leave me in the hanging here. Can I use for all quantifiers? Yeah, sure. Well, let's see. Well, what we could do instead is, well, instead of having to work over both of these formulas in the same formula, I just have a for all that handles both of them in one formula. Okay? So then, because of the for all and the solver that we made earlier up here, where we can delete the space to solve it, then we can actually achieve polynomial space. So here's what we're going to do instead. So this is bad because, so I should say does not work. Not necessarily in poly space, because I'm doubling the size of the formula anytime I want to dig one level deeper, which is not what I want. So here's what we're going to do instead. So C1, C2t, the thing I still want to solve. Well, I still want to know if there's a mid, right? I got to know if there's one middle config such that I can get from the first to the second and from the second to from mid to the second one. So I want to still know that. Well, I want to handle, well, I want to go from C1 to mid and mid to C2. Well, I could just have a for all quantifier that looks over both of those possibilities and then has a subformula that says, oh, the formula must handle both of them to be true. So here we're going to say, well, for all, well, I have two things I need to look at here. The starting config and the ending config. It's C1 mid or mid C2. So here I'm going to say, well, for all pairs of the form start and end, in the set, C1 and mid, and the other pair is mid C2. Well, for all pairs, well, there's only two pairs. Well, then all I just ask, is this formula true? So from phi, from start to end, taken at most t over 2 transitions. So does there exist a middle configuration such that for every way to assign start and end with C1 and mid to C2, both of those ways have to be true, then I just check for both of them, is that little subformula true? Well, do I still achieve polynomial space? The trueness is still the same, but do I achieve polynomial space here? Well, anytime I try to dig down one deeper, I gain a for all quantifier there, but I only gain one. I don't gain two. So by gaining one there, and the rest of the formula is, there's just one subformula, so that must mean I don't have this doubling behavior every time I dig down. So in fact, I get polynomial space now, which is kind of cool. So then we just ask, I'm not going to write it, but all you just ask at the end is the same as the Cook-Levin theorem, where you just say, can you get from the start config to, sorry, as Savage's theorem, can you get from the start config to the end config in the maximum possible number of transitions? So the correctness is almost exactly the same as Savage's theorem. But we needed to be a little bit careful in the amount of space we actually used for the reduction. So this takes poly time. Because the formula is only polynomial size in the original formula size. The original machine size, I mean. So it takes polynomial time and hence poly space. So the details, I don't expect you to understand every single detail here. But the key here is that we can achieve a reduction like the Cook-Levin reduction and mirroring some things about Savage's theorem. So Cook-Levin is kind of similar for the first part, and then the second part we needed to be a little bit careful about the amount of space we used for the reduction. But that's all we really needed to do differently than the Cook-Levin theorem. Okay, so the real upshot here is that we finally have a P-space complete problem. Okay, any questions about that? Yeah.
Can you reiterate about, because we're taking every problem in L and showing that you can return it to TQBF?
Every problem in P-space, you mean? So
P-space, L
yeah.
and P-space.
Mm-hmm.
So where are we taking a P-space problem in? Is that the conflicts part?
Yeah, so P-space is L right there.
Yeah.
And then we're showing for an arbitrary L, so for any language in P-space, it reduces to TQBF.
And those conflicts are representative of L.
Yeah, of this machine on some input. Yeah, so it's only a sketch. I'm not doing the entire thing. So it's very similar to the Cook-Levin theorem, where we built a formula based off of this machine and this input.
So what is the input?
So the input is going to be a string W of some length, but there's no need to really consider all the details here, because if we wanted to consider the details, we definitely could, but there's no need in this case. To reiterate everything that we did for Cook-Levin would be, yeah. Because I want you to understand the general overview of why that this is P-space complete, not all the details.
So then it would be like, the general overview would be that by using overall quantifier,
Yeah.
divide, we can store
Right. Mm-hmm.
like each stack trace.
Yeah. So
Finite amount of time.
So we're not doubling the size of the formula every time, and so therefore we can achieve polynomial space. Because and in fact we can do this in polynomial time, because I just look over each of the pieces and I just dig my way down, and then I just build a little formula for each one of them, and I don't increase the size of the formula beyond polynomial time. Polynomial space, but you can do that in polynomial time. And so therefore the reduction takes polynomial time in the size of the whatever input was given to us. Other questions? Okay. So now I got to figure out what to teach next. Okay, that would be kind of cool. So remember how we defined P, NP, and P space, right? We looked at this class either time or this class space. And we said that time of f of n, for example, is all the languages that can be decided in O of f of n time or O of f of n space, right? And so, for example, we saw that, we saw that space of, say, n, so the things I can do in linear space, how does that compare to things that you can do in, say, n squared space? Well, it seems like if I give you more space, could you do at least as many problems as you did before? Yeah, you could just ignore the rest of the space, right? And so therefore, this must be a subset relation, right? So there are at least as many problems in space n squared versus space n because I gave you more space. But what might be a natural question about this? Well, what if they're equal? What if, for example, you have some algorithm that runs in space n squared? Maybe there might be a cool way to convert any space n squared algorithm to one that runs in linear space, which would be really nice because if you have, say, bubble sort as an example, which runs at n squared time, could you convert that into maybe n log n time, or convert any, say, all pair shortest paths problem that runs in n cubed time? Could you convert that into a faster algorithm no matter what? Right? That might be a cool thing to do. Or is it always the case that there's some problem in space n squared, let's say, that you cannot solve in linear space? So there's kind of like a hierarchy of problems here. So which of the two cases do you think is the true one? Where like you have like space n equals space n squared, or the other one where there is a difference between n squared and linear space? That there actually is a difference. So that's actually what we're going to prove here. So I gotta do one definition first. So we say a function f, and it doesn't actually matter here, but it's from the natural numbers to the natural numbers, but any function really that takes integers, where f is at least log n, is called space constructible if we can compute f of n in order f of n space. So if it doesn't take too much space to actually compute that value, then we say it's a space constructible function. So for example, n squared is a space constructible function because if you take in integer n, just multiply it with itself to get n squared. And you never need more than a constant times n squared amount of space to actually compute that value. Okay, so therefore that's a space constructible function. And in fact, pretty much any function that you think of like a natural function, like n or n log n or n to the 1.5, n squared, n cubed, all those are space constructible. Okay? There are functions that are not space constructible, but we're not going to consider those. The only reason to have this definition here is because when we showed that there's a difference between these two classes, I want to know what the actual value is, but I can't have the function be take so much space to actually compute this that I'm using more space than I'm allowed in the first place. So I need to be able to actually compute that value with the correct amount of space, not too much space. And the reason for that is we want to, if we're going to try to, so if we're given some a machine that runs in space of n, then what we want is to build a machine that is in space n squared, but differs from every single machine that runs in space of n. And how we do that is we need to mark off on the tape what this value f of n is. Because if we use more than f of n space, then the machine, we just reject immediately. So we actually need to have a space constructible function here. Okay, so the theorem we're going to show is, so there, I'll do it formally here. For any space constructible function f, there exists a language L that can be decided. So I can't use time here for a very important reason, which you'll see. In O of f, big O f of n space, but not in little o f of n space. How many of you are not familiar with little o? Okay, so some of you. So can anyone tell me what little o means? So here, if you look at the formal definition, it's just there exists an n0 for which the f of n is strictly larger than the function which is little o of that thing. Whereas for the big O is at least as large, so greater than or equal to, where here is just strict inequality. So here, basically, if you change the amount of space even just by a little bit in the asymptotic sense, then you're going to get strictly more languages than with fewer languages, with little o. Okay, so how are we going to even prove this? Well, let's see. So we're going to actually, so it could be the case that this language L, we can prove that it exists, but we have no idea how to build a decider for it. That certainly could be true. But in fact, here we're going to make a decider for this problem. So we're going to build a decider D for L running in big O f of n space, but not in little o f of n space, which is what we want to do. Okay? Cool. So how are we going to build this decider? Well, whatever input it gets, let's just consider input W. Well, as I mentioned earlier, we gotta compute the value of f of n, where n is the length of the input, right? I need to mark that off on the tape and then ensure that we never use more space than that, whatever that amount is. So as the first step, we're gonna let n, so we're gonna compute the length of W. So let n be the length of W. So then compute f of n and mark that cell on the tape. If we ever use, if we attempt to use more at any point, reject. So we're just going to compute the maximum number of cells that you're allowed to use. And then we're just going to, if we try to use more, then obviously it does not run in f of n space. So therefore we reject. Okay. So this step may seem a little weird, as a lot of things in the class might be. But I'll explain why it is in a second. So if the input W is not of the form some Turing machine with a 1 after it and then any number of zeros after it. So if it's not of that form, we reject. And I'll explain why we do that in a second. But now, the reason for that is that we want to have a machine that now we guarantee runs in f of n space because we marked that off on the tape, right? We marked f of n on the tape and then we just simulated this machine M. Well, if M ever tries to use more than f of n space, we just said in step 2 we reject. So M, therefore, must run in f of n space. Okay? And then we're going to try to argue why D does not run in f of n space. It uses strictly more space in the asymptotic sense. Okay, so then all we're going to do is run this machine M that the input was part of, run M on W for at most, so this is not exactly correct, but it's close enough. For at most to the f of the largest possible number of transitions, because that's the number of configurations that could occur within those f of n cells. So with at most that many transitions. If attempt more, then we reject. Then as the last step, output the opposite of M, of what M says, I should say. So I'm going to get back to this after the break, but a quick proof of why this works. Since we have this 1 and zeros after it, I'm using more space than what M has here. Then since we're outputting the opposite of what the machine said, it must disagree with every machine running with at most f of n space because it outputs the opposite. Okay, so therefore it's different from every machine that runs in f of n space, and it uses more, so therefore it uses strictly more space, so we just found our language that we need. Okay, any questions before we break? Cool. Let's